This is Dr. Carroll, and welcome to a video about heaps. So heaps are a natural implementation for a priority queue. And heaps have two main properties which we're going to discuss, namely a structure property and a heap order property. First off, heaps are a complete binary tree. Make sure you know what that is. So this property is the structure property of it. We need to make sure that we're always a complete binary tree, or the operations just won't hold up, or our efficiency will degrade. The other property is that the value of a node is greater than or equal to the value of the children. And so this is a recursive property, not surprisingly, since it's a tree. And that this is the heap order property. And now notice that this definition is similar to that of a binary search trees, but the ordering of the children is relaxed. From this definition, we don't know if the left child or the right child has a value which is greater than the other, and we don't care. Things will work out. So let's see an example. Here we have a heap, because it could fit in. It's a complete binary tree, and each node, its value or its key is greater than its children's key. And we apply that recursively. 13 is greater than 10 and 11. 10 is greater than 3 and 9. 11 is greater than 11. 11 is greater than 7, and we have a heap. And so this is stored in an array for efficiency. And so we would put the root node in index 0 here in the first element, and then we'd go its children in order, and then would go to the next level and would fill it in. Notice 10 is here, 11 is here, and notice 3 is here, and we just complete it. And for a complete binary tree, it fits very well into an array. Here we have not only a complete binary tree, but a full tree at that. And the numbers here are not the key values, but the index that correlates with the array. Notice that, so the highest priority item goes in the root, and then so forth. So if you might need to refer back to this if you were going to use if you're referring to the array structure and trying to map that to a complete tree. Okay, there's our examples. And as mentioned, we're going to use an array to implementation. Now let's talk about the operations. Well, they're the same as a priorities queues operations. We have top that returns the item with the highest priority. Well, that's easy. It's just the first item in the array. Great. Insert. It inserts an item. Okay. Well, there's two general steps we need to do. First, we need to add the last index. We need to add the item to the last index of the array, and then resize if appropriate, probably. Okay, so we put it at the very end of the array. We've maintained the structure property of the heap, but we've violated the heap order by doing this. So before we can declare insert done, we need to do step 2, and that's bubble up. This is also referred to as percolate up in some texts. So let's talk about what is bubble up. And so if we're going to bubble up, we're going to start at some index, and we're going to iteratively swap a child and its parent if the child's value is larger than the parent's. Okay, because we need to maintain the heap order property. Okay, so we can calculate the parent, and notice, because of our structure property here, the parent is really easy to calculate. There's no pointers involved. We just take our index, subtract 1, divide by 2, and there we have it. We have our parent value, our parent index. That's very easy. And so we can say, well, while our index is greater than 0, while we're not at the root, what we're going to do is we're going to see if we need to swap, if our value is greater than our parent's value. And if it is, well, then we'll swap the two. We'll update the index we're pointing to and what the child is, and then we'll just continue. And when we don't need to swap, then we're done, because we started with a heap and now we've obtained a heap. So that's bubble up. Make sure you know how to do that. Pop, if you'll remember, removes the item with the highest priority. Okay, and this is going to require 2 steps. Finding and removing the item with the highest priority is easy, but fixing the heap is going to take a little bit more effort. So step 1, we're going to overwrite the first item with the item from the last position of the array. Okay, we're going to take what's in the last position of the array and put it in the first position. Well, that's easy, but we've maintained our structure property here, but we've violated our heap order property. So we're going to fix that, not surprisingly, with a bubble down, or sometimes referred to as a percolate, okay, or a percolate down to maintain the heap order property. Okay, so we're going to start at the root index for bubble down, okay? And so while the index is not at the last level, because once we get to the last level, then we're done. If it's a leaf, we set the child to the node with the largest value, because we're not quite sure which of the 2 children it needs to be bubbled down with. So this item, we need to check if it's a lower priority than one of its children. So we just need to figure out which child has the highest priority, and then if the priority at index is smaller than the priority at child, which is the larger of the 2 children, then we'll swap. And if it's not, great, we're done. We have a heap. And then, but if we're not done, we need to update our index and child indices. Okay, so that was an outline pseudocode. So now let's see some code, some C++ code for it. So again, child, you notice, is calculated very similarly to how a parent is calculated. Very easily. Double it and add 1. That's it. Simple, fast. That's because we have our complete binary tree. So then while the child is less than the size, we're still dealing with children that are in the array. We choose the child with the larger value. And so if and we need to protect against the case that there's only one child here. So we need to make sure that the right child is in the array, and if it is, and that right child has a priority value higher than the left child, then we're just going to increment child to point to that other one. Now child is the index of the larger of the 2 children. So now we can say, hey, is our index, is its priority less than the larger priority of our children? And if it is, we swap. Okay, and then if we're not, we can be done. And then we update the child and the index and the child, and there we go. Let's see, let's put this in here. Else break for efficiency reasons. All right, let's talk about the efficiency of these operations. Top here is going to be order 1. We're just going to return the highest priority item. That's easy. It's at the top of the heap, the first position in our array. Now insert is going to be a little bit more complex. So worst case is we need to bubble down the entire path from leaf to root. Okay, so that's the path. And so that's going to be, it's a complete binary tree. So hey, great. That's a log base 2 of n. So worst case is it's log n. Average case is we're going to need to bubble up about part of the way from the leaf to the root. Well, that's still log n, okay? And so that's great. Insert log n. Sounds great. Let's see if we can, what we get with pop though. Make sure we're not doing an unfair trade-off here. So worst case is we need to bubble down the entire path from root to leaf. Okay, the entire path, oh yeah, again, it's log n. Average case is it needs to bubble down part of the path from the root to the leaf, and that's going to be log n as well. Let's quickly talk about different types of heaps. We've been talking in this video exclusively about max heap, where the highest priority is the largest value. But there's also something called a min heap, and they have their place, where the highest priority item is the smallest value. So the smallest value would then be found at the root of the heap. Let's quickly talk about some disadvantages of heaps. So that they perform things in log n time, if not constant time. That's great. But what if we didn't want the highest priority item? What if we're trying to find something else? Say, worst case, the lowest priority item. Well, that could take us order n time. And so they're not appropriate for methods that need to deal with that or need to be able to get any item that's not the highest priority item. And that completes the video for today.